Welcome everyone to 7.4, Integration of Rational Functions by Partial Fractions. So this is a great section, and it actually relies on both algebra and calculus. So the algebra portion of this is going to be breaking up these fractions in a new way, and then we're going to have to solve systems of equations. So that's kind of the algebra aspect, and then once we have that, we can apply the calculus to actually evaluate out some integrals. So let's get to it with a definition. So this section is called Integration of Rational Functions by Partial Fractions. I should probably tell you what are partial fractions. So this is a technique that can be used to help integrate many rational functions. So it essentially is finding a common denominator in reverse. Okay, so to demonstrate this, look at this example. So use the fact that 2x plus x over x times x plus 1 is equal to 1 over x plus 1 over 1 plus x. So if we assume that is true, forget about how I figured this out for the time being. If we assume that this is true, then the claim is that now we can integrate 2x plus 1 over x squared plus x. Notice that this is the same denominator, just distributed through. Okay, so let's use this fact to instead integrate 1 over x plus 1 over 1 plus x dx. Okay, and while this thing over here we may not have known how to integrate, 1 over x we can certainly integrate, and 1 over 1 plus x we can certainly integrate. So the integral of 1 over x is the natural log of the absolute value of x, and the integral of 1 over 1 plus x is the natural log of the absolute value of x plus 1, plus my constant of integration. So this is the idea of partial fractions, is finding this common denominator in reverse. So let's go over the general technique then for how to apply partial fractions. So partial fractions deals with rational functions, and that is a polynomial over a polynomial. This first case, I'm only going to deal with the degree of the numerator, f, less than the degree of the denominator, g. In this case, we want to first factor the denominator. And we're going to factor it into linear terms and irreducible quadratic terms. The second step is that we're going to express the rational function as a sum of partial fractions of the form a over, and now we have linear terms, so this is going to be ax plus b raised to some power I, or the irreducible quadratic terms will be of the form ax plus b over, and again, an irreducible quadratic should look at the form ax squared plus bx plus c raised to some power I, where I takes on all the values less than or equal to the power of the factor. And these should be whole numbers or positive integers, actually. The third step is to solve for all unknown constants using algebraic techniques for solving systems of linear equations. So the claim is this will come down to solving systems of linear equations. All right, let's do one of these examples out in completeness, right? So we're not going to assume that we know what the answer is for this one. So evaluate, and we see we have a nice rational function. The degree of the numerator is less than the degree of the denominator. And so the first step is to factor the denominator. So I can factor this. It looks like it'll be x minus 3 times x plus 1. The second step is that I'm going to assume that I can break this up in linear terms or irreducible quadratics. In this case, there are no irreducible quadratics. So this is just going to be, let's see, some constant a over x minus 3 plus some constant b over x plus 1. And notice because those have powers 1, right? X minus 3 has power 1. X plus 1 has power 1. Well, I has taken on all the values from 1 to 1, essentially. So that's it. Now I need to do algebra. So I'm going to solve a system of equations. So I'm going to assume, right, that this is true, that there's some a and b for which these two functions are equal. So these are equal in terms of functions. Okay, then we have to think a little bit. Let's go ahead and multiply through by the LCD. Okay, so there's a couple different ways we could go about solving this. We could get a common denominator first or whatnot, but I'm just going to multiply through by the LCD. So if I do that, well, the left-hand side just becomes 5x minus 3, and then the right-hand side, well, the x minus 3's cancel out for the a term, and the x plus 1's cancel out for the b term. So I'm left with a times x plus 1 plus b times x minus 3. Go ahead and distribute that through. And we're going to collect like terms. So we have an a and a b next to the term with the x. And then we have the constant term will be a minus 3b. So now if these are equal as terms of functions, well then it's true that a plus b must equal 5 and a minus 3b must equal negative 3. Otherwise they would not be equal as terms of functions. So here's where we get our system of equations. A plus b equals 5 and a minus 3b equals negative 3. So now we have to think back, how do we solve systems of linear equations? Well, I'm going to use linear combinations and subtract the second equation from the first equation, because you can see then the a's cancel out. The a's cancel out, and then I get b minus negative 3b, so that's going to be 4b. And then 5 minus negative 3, that's going to be 8. So therefore b equals 2. And if b equals 2, we can plug that back into the first equation and see that a must equal 3. So we were able to solve for these constants. We were able to figure out that b has to be 2 and a has to be 3. So therefore, we can rewrite this as the integral of 3 over x minus 3 plus 2 over x plus 1 dx. And we've successfully applied partial fractions. Now we're left to the calculus part. And the calculus, so we will integrate. We get 3 times the natural log of the absolute value of x minus 3 plus 2 times the natural log of the absolute value of x plus 1 plus my constant of integration. Oops, not dx. Plus my constant of integration, c. And that is our final answer. All right. Let's do one now where we have i's taking on different values other than just 1. So in this following example, we can see that we have this linear term x plus 1 is now squared. So when we go to apply partial fractions, remember these i's have to take on all the values less than or equal to the power of the factor. Okay, and this factor, x plus 1, it has power 2. So we need to have it take on both 1 and 2. So that means we're going to have the integral of a over x plus 1 to the first power plus b over x plus 1 to the second power. So now it takes on both 1 and 2 dx. And I'll go ahead and erase this. This is just to show you here. Okay, so let's assume that this is true, that we can split it up in this way. Then again, I need to do some algebra here. So let me use my green pen and assume that this left-hand side, x plus 4 over x plus 1 quantity squared, is equal to this right-hand side. So a over x plus 1 plus b over x plus 1 quantity squared. And then I'm going to multiply through by the LCD, the lowest common denominator, right? And that's going to be my x plus 1 quantity squared. And so on the left-hand side, I get my x plus 4. On the right-hand side, well, you can see with the a's, only one of the x plus 1s cancel out. For the b's, they both do. And again, I want to group these things with common terms, right? So all the things with x's go together, and all the things without x's, the constant terms, go together. So if these are equal as terms of functions, we have to have a equals 1, and we have to have a plus b equals 4, which that means that then b has to be equal to 3. So really, the solving of this system of equations was not that difficult. That was a pretty nice one, all things considered. So a equals 1, and b equals 3. All right, now I have to think about how do I integrate this. The claim is that I can. Well, integrating 1 over x plus 1, that's the natural log of the absolute value of x plus 1, minus, plus 3. And when I integrate this, I'm going to get, well, remember the power goes up by 1. This is really like x plus 1 to the negative second power. So when I integrate that, that's going to become x plus 1 raised to the negative first power. And then I'll need a negative. Check by taking the derivative really quick, and you'll see that this is correct. Add my constant of integration, plus c. And there we are. That is my final answer. All right, I think that's probably a good place for us to take a break. When we come back, we have 2 more tougher examples that'll take the entire video. So stretch your legs, and I'll see you here in a few minutes.